Okay guys, so this video is based on what is the Damkohler number, and we're going to be using two different variables, and the two variables are going to be the time constant, or the space, and the space-time. Sorry, time constant is space-time, so we're going to be using space-time, so I'll have to describe that, space-time, and yeah, this should be good enough to discuss the Damkohler number. Okay, so what is a space-time? We're going to need to know what this means. So let's take a CSTR, right? I try to draw it as best I can, just like this. Okay, there we are. And so the space-time tells you how much time it takes to process, or basically to move, amount of reactant. Basically, how much time does it take the contents to move through the reactor? So if let's say you have, I don't know, this much liquid going in, how much time is that liquid going to spend before it comes out? The amount of time it takes to process 1 unit reactor volume. So, and you're going to see this is going to rise from our actual general equations. So in the previous video we came up with this. Pretty simple derivation. I won't, for the sake of time, I will not derive it again, but it's in the previous video. Okay, so we had this, right? FAO x over negative RA. So we're going to make the time constant basically. So the volume is equal to initial concentration times the volumetric flow rate. Basically, this is a true expression. The molar flow rate is the same thing as the concentration times the volumetric flow rate. So if you plug that in, this is what you get, right? Now, I want you guys to divide Q to the other side, the flow rate to the other side. So you have volume over Q is equal to CAO times X over negative RA. So let's take this, let's take it to the side. Let's analyze the units of this, right? So what you're going to find if we're using SI units, you're going to have m cubed, meters cubed, over meters cubed over seconds. And that's the same thing as saying seconds, right? So what does it mean? What does it physically mean? Because that's very important. Well, if you divide it like that, it's telling you, based on the flow rate going in, how much time it takes to process 1 unit of volume, or 1 reactor volume. Time to process 1 reactor volume. And it's basically indicative of how long the material spends in the reactor. And the longer the material spends in the reactor, the more reactions you're going to have, or the farther the conversion is going to go. And that's the idea. Let's analyze that for a second, right? So we have T is equal to CAO X over negative RA, and X is your conversion. I'll use colors here. X is your evil conversion. Then what you're going to see is, as X goes up, well, guess what? T has to go up. Sorry, I should use the colors. Evil conversion goes up because T goes up. It's really the way to look at it is that the space-time goes up. You let the material spend more time in the reactor, and the conversion has to go up. So that's what the space-time means. So what is the Damkohler number? Well, it depends on your reaction, what you're going to plug in for here. So let's take what we got so far, T, which is equal to V over Q, which is equal to the right side of this equation. I like to write it this way because you're remembering where you got the space-time, or tau. So what happens here? So you look at it, and you have to figure out what type of reaction order do you have. For KCA, first order, second order, etc. So the Damkohler number is much different, or a little bit different, for first order than it is for second order. So let's use first order first. So V over Q, which is going to be equal to CAO X, plugging in for negative RA, we'll use KCA, which this is also going to be equal to KCAO 1 minus X. So I might just put that straight in. There we go. So CAO's cancel, right? So I want you to multiply K to the tau side. Okay, I'll explain why that's even good to do. Why even do that? Like, why even name it the Damkohler number? So dA for first order reaction is equal to tau times K. And it's basically written like this. So in industry, this is what they'll use. But why? Because if you looked at it, let's expound tau and DA1 and look at the whole thing as a collective whole. These are all the physical parameters. They don't really change. I mean, you can change Q, you can change V, you can change K depending on the temperature, but they're indicative of physical parts of the process. They're not changing throughout the time if the conditions are held still. So the way to look at that is you have all your physical parameters on one side and you got your result on the other. It's really saying, well, if I change my Damkohler number or your physical parameters, sorry, I'm drawing a lot of arrows today. There you go. So if you change your physical parameters, volume, flow rate, and the temperature, and hence decay, then your conversion is going to change. So you can plot that out and get very useful information from that. So before the video ends, I want to go over how do you get the Damkohler number for second order reaction. Because remember, we use this. Really this, but same thing. So let's do it. So we know tau is equal to V over Q, right? Which is equal to CaOX negative RA. Or, sorry, we'll use just, no, we can't use that one yet. We got to keep the RA in. CaOX negative RA. If you're wondering where I'm getting that from, it's right here. Okay. So we're going to plug in second order reaction. CaOX negative RA is K CaO squared 1 minus X squared. Where did I get that from? Well, I know that negative RA is equal to KCa squared, and negative RA is going to be equal to KCaO squared 1 minus X squared, to put it in terms of conversion. Okay, so let's cancel this one out, cancel the exponent. Alright, keeping that alive. We look like this. So remember when I said that we wanted to have conversion on one side and all the physical parameters on the other? Well, here we go. So take both of these and do this. Right? And that's going to leave you with this. And as you can see, the Damkohler number for a second order reaction is different. Tau K CaO. However, it's still a function of parameters, or sorry, it's still a variable of parameters. I'm having trouble tonight. So basically, when those parameters change, your basically results of conversion or your reactor's response will be different formula than first order. So you'll use this case for second order CSTRs. Now Damkohler numbers can also be used for other things too, like PFRs and such. Basically grouping the physical parameters on one side and the response on the other, which would be conversion. I hope you found this video useful. Hope to see you in the next. Yes, hope to see you in the next video. Sorry, a little distracted.